Tenemos el gusto de tener con nosotros al profesor Dr. Bruno Douine de la Universidad de Lorena en Francia. Y va a presentar su tema de superconductividad para la fusión. I'm going to switch to English. So we have the pleasure to have with us Professor Bruno Douine from the University of Lorraine in France. He's going to talk about the superconductivity for fusion. We have 1 hour talk, and this is our pleasure to have you in the Institute of Engineering of the National Autonomous University of Mexico. Thank you very much. The floor is yours.
Thank you. You hear me? It's okay? So thank you, Frederic, for this nice introduction. Thank you to invite me to present one part of my work. Just the context of this presentation. So I am professor of electrical engineering at the Université de Lorraine in a lab, groupe de recherche en énergie électrique de Nancy. We are working on applied superconductivity for electric energy applications. You have to know also that in France, we have big resources on nuclear in general, fission in general, nuclear plants, atomic energy companies, and so on. And now, nowadays, we have some new attract on fusion. In France, we have also in atomic energy company some reactor, fission reactors and fusion reactors in the south of France, for example. So today I present the superconductivity for fusion. You have to know that for fusion we can make fusion with different type of systems. So my plan for my presentation is at the beginning I will present the fusion, some physics on superconductors and superconducting material for fusion. This slide is from my colleague Dr. Jean-Louis Duchateau from Atomic Energy Company, and explain how is the fusion reaction with deuterium and tritium. So in the case of deuterium and tritium, if you have a very high temperature, around 100 millions of degrees Celsius, you can have some reaction between these two ions. It produces a lot of energy, fusion energy, plus produce helium-4 and neutrons. And to know if it's possible to take energy for electric grid, for example, we have an amplification factor, Q, is the power of the fusion divided by the power you put inside the reactor, P exterior. So normally in the future, when they make the reaction in ITER reactor, fusion reactor, they could reach Q equal 10, but it's just, theoretical value. So it will be there, it will be in a reactor in ITER, perhaps in the next 10 years. But if you want to take energy for electric grid, for example, as nuclear plants, the value of Q has to reach 30. So, yes, there's a big difference between 10 and 30. This is why normally, in the case of ITER, after ITER, there will be a new reactor, demo, and they want to reach this value of 30. So to have this fusion, you need different things. First, very high temperature, 100 millions of degrees Celsius. At this temperature, the gas of deuterium and tritium is ionized as plasma, so very, very hot plasma. And because of this temperature, it takes confinement of the plasma in the reactor. And there are some different possibilities to confine the plasma in the reactor. And I will present only the magnetic confinement of the plasma. And in this plasma, you have electrons, ions, but confined by the magnetic field, for example. But in the case of neutrons, neutrons have no charges, electric charges. This is why neutrons are not confined in the plasma. So outside the reaction, outside the plasma, you will have some neutrons. And with these neutrons, you can change some materials in reactive materials. This is one of the problems of this kind of confinement. So one of the first fusion reactor was tokamak. Tokamak is from Russia. Okay, it's a word from Russia. And in the tokamak, the plasma is in the shape of toroidal plasma, like this, and is confined in this tor. And to do this, you need different coils. First, in the plasma, with the, as you see, the induced current around 1 megaamps in the plasma, with the green arrows, is this current in the plasma, displacement motion of electrons and ions, is induced by a central solenoid. The central solenoid is in the coils at green color. And in this central solenoid, you have AC current with very low frequency, around 0.1 Hertz, around in a period of 10 seconds. And in this central solenoid, the current is around 100 kiloamps. So very huge current. With this induced current, you produce poloidal magnetic field, green ellipse on the drone, but it's not sufficient. So you have the current of the plasma, produce poloidal magnetic field. So you have to add toroidal magnetic field, blue cycle on the drone, and this one is produced by the toroidal field coils with DC current inside. If you add poloidal magnetic field plus toroidal magnetic field, you produce helical magnetic field. On the drone, it's in the black lines. And because of this helical magnetic field, you produce helical motion of the ions and electrons. And this is why we have confined the plasma of ions and electrons in this tor. You have also some poloidal field coils, big field outer poloidal field coils. Just these coils are to maintain the position of the plasma and to stabilize the plasma. And in this poloidal field coils, you have only DC current. So on this on this figure, you can see the toroidal magnetic field produced by the toroidal coils, the induced current producing induced poloidal field, and the total field, helical magnetic field. So to reach the very high temperature, the current of the plasma is not sufficient. You have also you need also radio frequency heating to increase the temperature to this goal of 100 millions of degrees Celsius. And for this, you have some radio frequency antennas at different frequency, megahertz, 100 of megahertz for ions and electrons, gigahertz for quick electrons and ions, and also hundreds of gigahertz for electrons. In the tokamak, in the fusion, there is some characteristic of this plasma. First, you have the current of the plasma, IP, and this plasma is linked to the magnetic field. So if you increase the magnetic field, you increase the current in the plasma. You have also the little radius of the plasma, A, and the big radius of the plasma, R. So the current of the plasma depends on these different things. You have also the fusion power, and the fusion power depends of the volume of the plasma. If you have a bigger volume, you have more power. It depends of the temperature. So if you increase the temperature, you increase the power. And depends also of the density of particles. If you have more particles, more ions, you have more power fusion. And this reaction depends of empirical merit factor. And this merit factor around is just linked to the power of the fusion. And this power of the fusion, this fusion power, is linked to the radius, the big radius, and then is linked to the magnetic field inside the plasmas. So this is why if you increase the radius of the plasma, you can reduce the magnetic field, or in opposite way, if you increase the magnetic field, you can reduce the radius. Okay? This is why there is two possibilities at this up to now. Is large reactor like ITER, where the magnetic field of the plasma is between 1 Tesla to 10 Teslas. And now we have a new possibility with HTS, high temperature superconductor. You can reach more than 10 Tesla inside the plasma, and you can reduce the radius. Okay. This is a slide on tokamak. So the beginning of tokamak was during the 80s and 90s. So this is one of the toroidal field, toroidal coils of tokamak Tor Supra in the south of Paris, made by atomic energy companies in Cadarache in the south of France. In this case, they had 30 tons of niobium titanium at a temperature around 2K with superfluid heliums. It worked between the end of the 80s to the beginning of 2000. After Tor Supra in France, they produced a new reactor from Tor Supra West, and at the date around the 19th of February 2025, they produce a plasma at 50 millions of degrees during 22 minutes. It's a world record for fusion. But it's not sufficient to have a real fusion reaction. It's just the beginning of something. So after Tor Supra, they imagine to make a new reactor, international reactor, okay, ITER. And you can see, for example, on the drone, I can show you here, you have different reactors, Tor Supra, TS, so you imagine the size of the toroidal coils here, and here you have the size of ITER, much more. So the radius, the big radius of the ITER is much more than toroidal Tor Supra. This is why if you increase the radius, you can have magnetic field lower, and you can produce fusion. Normally, the ITER consortium will make the first experiment of big temperature around 2030. It takes a long time. It takes also a lot of money, billions of euros or dollars, to make this fusion reactor. On this drone, you can see toroidal field, cryostat, because you have to be at very low temperature. We also blanket. This blanket has to support very high temperature. This blanket has to support the neutrons. And you have also diverters, and diverters has to take the energy from the plasma to, for example, heat some water. So here you have a drone of the toroidal field. Here, produce toroidal coil, produce toroidal field. And you have also the radio frequency antennas to increase the plasma in the plasma chamber. And you have also the diverter. The diverter is to extract the power, to heat some water, and go this energy to turbines and so on. And you can also catch the waste of the reaction. This is the toroidal field coils, and you have also central solenoid. So you have to remember that central solenoid at the center of the reactor induces plasma current. This is why in this central solenoid you have AC current with very low frequency. And you have also poloidal field coils that just here to shape the plasma, to have a good plasma shape, and to contribute to the plasma stability. So where is ITER in France? ITER is in the south of France, near Marseille, if you know. And it is very close to CEA Cadarache. So CEA Cadarache, donc Atomic Energy Company, makes, for example, Tor Supra. So you have a lot of expertise in this region of France. In CEA, for example, in Tor Supra, they have many reactors in CEA Cadarache. And you have also a very huge amount of electric energy with a very high voltage electric line. Because you have to know that for the reaction in ITER, you need around 1 gigawatt of energy near the ITER reactor. This is why you need very high electric line plus fission reactor, nuclear plants, not too far. Here you can see on this photo, on this figure, in March 2022, they just produce the enceinte of the reactor, and they just put the central solenoid, okay, at this time. Afterwards, they put these big toroidal coils. You imagine the size, it's around tens of meters, just for the toroidal coils. And it was put these last 2 years in the reactor. After ITER, so you have to imagine that ITER will not produce energy for the electric grid. They just want to produce reaction. They want just to produce fusion during few minutes. But just few minutes is not sufficient to produce energy for electric grid. This is why ITER is just to show that it's possible to make fusion on Earth, okay, with deuterium and tritium, okay, and reach this 100 millions of degrees. So after ITER, they want to produce a real fusion reactor. This demo has to produce energy for the electric grid. And so at this time, in the future, 2050, 2060, they want to produce energy for the electric grid in France. And one of the questions they have, so you have to know that one of the boss of this demo design was Jean-Luc Duchâteau from Atomic Energy Company. And for the future, they want to just to design the demo reactor, and the question is, the demo magnet system is just an extrapolation of ITER magnets, or you have to create something else, okay? For example, they want to know if it's possible to put HTS material, high temperature superconductors, in this kind of new reactors. So this is the following, demo is the following of ITER. You have to know that in the case of ITER, you produce helical magnetic field with the central solenoid with AC current. Okay, it's not so easy because, for example, you have AC losses in the central solenoids. So it's one of the problems. And with the poloid coils, you have to stabilize the plasma. This is why there is another option, especially, for example, in Germany. They want to produce helical magnetic field, not with the sum of different fields, but just by the shape of the field of the coils. So you have in the stellarator no induction transformer inside the stellarator, but you have very complicated coils, and the design and the building of this coil is very, very complicated. So they achieve this, and they make the first experiment this year. So the name of the stellarator in Germany is W7X. It's another option. So I will go to the physics, some basics on physics of superconductors. So you have to know there is two features of superconductor. The main features of superconductor. The first one is there is no resistance if the temperature of the superconductor is below the critical temperature Tc. For example, on this figure, you have the resistance of YBCO sample versus the temperature. So in the case of YBCO sample, here you have a critical temperature around 90 degrees Kelvins. The second feature of the superconductors is the Meissner effect. What is the Meissner effect? So if you have a superconducting sphere plunge in the applied magnetic field, the line in black, if the critical temperature, if the temperature is below, it's above the critical temperature, there is nothing, okay? So you don't change the magnetic field lines with the sphere of superconductor materials. But if you decrease the temperature below the critical temperature, there is some very high current at the surface of the sphere in opposition with the applied magnetic field, so producing induced magnetic field. So you have in the sphere no magnetic field. So there is an opposition between the applied field and the induced field. The name of this is Meissner effect. But in reality, in application, this Meissner effect is neglected because it's only for very, very low magnetic field. In reality, if you have more magnetic field, applied magnetic field, you need another possibility, another reaction of the superconducting materials. So, for example, on this figure, you have a cylindrical, infinite cylindrical of superconducting materials, and you apply some magnetic field HA in the same direction of the axis of the cylinder, okay? If the applied field is very low, so below HC1 is the first critical magnetic field, it's Meissner effect. So you have just supercurrent in the little surface, little volume, very, very, very small length, thickness of the superconducting material, but very high current, more than 1 megahertz square millimeter. But the problem of this HC1 is very low. For example, it's around 1 millitesla at liquid nitrogen. So it's not very useful for application in the motors or in cables and so on. This is why for application you need a new current. I call him volumic current. And this volumic current in the volume of the cylinder is linked to the real critical current density. So if you increase the applied field and you have more than HC1 but less than HC2, if you have less than HP is the full penetration magnetic field. In this case, H2, you have more than HT1, but the critical current or the volumic current doesn't reach the center of the cylinder. So you have volumic current in opposition with the applied field, just in a region between the center and the surface of the cylinder, and you have zero field inside. So you have three regions. External part, you have applied field. Internal part, you have no field. And between, you have between these two magnetic fields. If you reach HP, so full magnetic field penetration, at this case, you have plenty of volumic current in the volume of the cylinder of superconducting material, but it's always a superconductor. And if you increase the applied magnetic field more than H3, you reach a new magnetic field, He2. If you have an applied field more than He2, no more superconducting material. You have a transition to normal state. Okay? So for application, for example, He2 at liquid nitrogen temperature is around 10 Tesla or more than 10 Tesla. At liquid helium, it's more than 100 Tesla. So it's sufficiently high to have all the application you can imagine for fusion, for motors, and so on. This is why, in general, we are, in general for motors, in my case, we are between 1 and 5 Teslas. It's much more than classical motors, for example. So to be superconductor, so the material has to be under a certain critical temperature. The magnetic field has to be below the critical field, Hc2, Pc2, we can say. And the critical current has to be lower than the critical current density. And there is a link between these three parameters. So you have, if you have the figure Jc versus magnetic field versus temperature, you can have a surface. If you have, you are below this surface, you are superconductors. If you are above this surface, you are not more superconductors. So, what kind of superconducting material we can use for fusion? Up to now, for fusion, they just use, for ITER, for example, for tokamak, for Tor Supra, West, and so on, they use just low temperature superconductors, LTS. In this case, the critical temperature is below 20 K. So, in general, we use just two types of materials, niobium-13 and niobium titanium. There is a big advantage of niobium-13 is the critical temperature, very high, we can say, 18 degrees Kelvin. The critical magnetic field is very high too at 4K, 22 Teslas. And the critical current density at 4K and 5 Teslas is around 10 kiloohms by square millimeter. And you have another one, niobium titanium. You have lower TC, lower magnetic field, critical magnetic field, and you have lower critical current density. But it's this one, niobium titanium, the more used in general. Why? Because niobium titanium is very easy to make coils, motors, cables, and so on and so on. Because it's like copper. In the niobium titanium cable or wires, you have a lot of copper. You have niobium titanium plus a lot of copper. So if you want to make a coil, it's like using coils, copper wires. So it's very easy to use. In the case of niobium-13, it's very complicated, it's more brittle, very brittle. If you have to make a coil, you have to make the coil, plus to go to the furnace, heat at very high temperature, and so on and so on. So it's not so easy to make wires and cables and coils with this niobium-13. But it's an obligation to use this kind of material if you want to reach more very high magnetic field and very high current density. But this is why they use in fusion reactor, like ITER, tokamak, both. For a low magnetic field around 1 Tesla to 5 Tesla, they use niobium titanium, but for more than 5 Tesla, they have to use niobium-13 at very low temperature. In the case of niobium titanium, they use niobium titanium wires with for poloidal field, for example. So in the case of colloidal field, the magnetic field on the niobium titanium wires is not so high because it's external, okay? In the reactor, you have to imagine you have a lot of field in the plasma, but not a lot of field outside the reactor. This is why we can use niobium titanium wires in the colloidal field coils. You can also reduce the acylosis filaments of the wire to reduce the losses, especially when you increase the current, you have some losses, so you have to decrease the diameter of the filaments. Less than 10 micrometers. It has been made for many, many years by, for example, Alstom in France. You need also, for very high magnetic field, niobium-13 conductors. For example, in the central solenoid CSMC, you have 40 kiloohms at 13 Teslas on the wires. It is produced by niobium titanium filaments at very low temperature, around 2K. And for the toroidal magnetic field coils, it is also niobium-13. In the case of toroidal field, on the wires you have around 10 Teslas and 80 kiloohms. So very huge magnetic field and current. So, in the case of the reactor like Tokamak, ITER, West, and so on, they use LTS. But now, in some lab, in some industries, in companies, they imagine to use new superconductors. Why they want to use new superconductors is to increase the magnetic field. And to increase the magnetic field, the only one possibility is to use new superconductor, high temperature superconductors. So on this figure, you have two kinds of HTS, BISCO and YBCO. The problem of BISCO, you have to put near the BISCO in wires, cable, and so on, you have to put a lot of silver, and the cost of this is very expensive. Plus, the critical current of this kind of BISCO wires is not so high, especially at very high magnetic field. This is why it's over. BISCO wires it's close to over. There's just a production somewhere in USA. So all the companies of fusion want to use YBCO wires. So you see that YBCO was born during the end of the 80s, the beginning of the 90s. And for YBCO, the critical temperature is around 90 degrees. This is very interesting for application in electrical engineering in general, because it's more than liquid nitrogen temperature. So we can imagine, and they produce now, so for example, a company like Nessence produce some cables at liquid nitrogen temperature. But at this temperature, 70K, is not sufficient to have very high magnetic field, critical magnetic field. This is why, in general, for fusion, they want to use YBCO wires, but at liquid helium temperature, to have a very high current density and to have very high magnetic field. What is the interest of this kind of HTS for electrical engineering application, included fusion? You have very high current carrying capacities at liquid nitrogen temperature, more than 500 amps by square millimeter. You can have very high magnetic field if you reduce the temperature, like in the fusion, 4K, 2K, more than 40 Teslas. It's easy to cool down at liquid nitrogen temperature because liquid nitrogen temperature is very simple to have, to take. The cost of liquid nitrogen is very low. It's less than agua mineral, okay, for example. What are the limitation of this HTS is the cost by meter. It's decreasing every year, but it's one of the problem. and it's very difficult to produce very high length, especially because it's coated conductors. Normally, you can have very easily 100 meters of these wires, but more than 1 kilometer in one piece is very complicated. Almost impossible. So, what kind of things you can have with HTS materials? You can have tapes, like YBCO tapes. You have a lot of factories make this kind of tapes, but you can also have bulks. With this kind of bulk, cylinder of a few centimeters diameter, you can produce permanent magnet. 5 minutes, okay. You can also make some magnetic shielding. And with the tapes, you can produce coils. Here you have a figure from my colleague Carmine Senatore, professor in University of Geneva in Switzerland. You have to imagine that in these HTS tapes, you have just 1 micrometer thickness of superconducting material, so very thick. And so if you have hundreds of amps by square millimeter in the tapes, you have millions of amps by square millimeter in the superconducting part. So very huge. Now, up to now, we have a lot of factories linked to fusion. Faraday factory in Japan, Fujikura in Japan. You have also some factories in China, in Germany, in America, and so on. So lot of factories, much more than before. And if you make the characterization of this kind of tape, with DC current, we have a very special behavior of this kind of tapes. If you put the electric field versus the critical current density, you have a special law between the electric field and the current density. We can say the power law between both, and you have mainly two parameters: the critical current and the value n, the n value. These two parameters depend of magnetic field and temperature. You have to know that there is a standard for this. In IEC, you have the reference on the figure. So you have also you need also the dependence on magnetic field and temperature of the critical current density. You can make also the characterization of the HTS tape by magnetic experiment. And one of the problems we have is to go from the characterization of the tape to the HTS coils. What is the critical current of the coil? We don't know exactly. You can have also quench. So what is the quench current? Which standard? We don't know. We have a discussion in IEC conferences on this. What is the interest of HTS for fusion? With HTS, you can produce at the same temperature, you can produce more field. Okay, for example, you can produce more than 20 Tesla. With low temperature, with LTS, the limit on the wires is around 20 Teslas. At very low, around 2 Kelvins. For YBCO wires, you can reach around 40 Teslas. This is why they imagine to produce very high magnetic field at this very low temperature with HTS. This is why in America, in China, in Great Britain, they imagine to make a compact reactor by increasing the magnetic field and decreasing the radius. This figure is from Tokamak Energy in Great Britain. So what is the advantages of HTS for fusion? You have more field. If you have more field, you can decrease the radius. If you have more critical current, you have less wires. If you have less wires, you have less weight. And you have less weight, you have less iron, concrete, and so on. So you reduce the cost of the reactor. So here you have two figures from two companies, Tokamak Energy in Great Britain and Spark Commonwealth Fusion System in USA. And you can see the size of this prototype is around 2 meters high. And for the coils, you need cables. And for example, this cable Viper, PIT Viper, is made with stacks of HTS tapes. And there is a study from my colleague Frédéric Trio on this kind of cables. Many problems. With this kind of stacks, you can have very high current capacity, very high magnetic field resistance, quench detection with integrated fiber optic detectors, modularity, flexibility, and so on and so on. And here in France, now we have a new project, Suprafusion program. We are included in this new project about HTS for fusion. Okay, it's very new, just it was beginning last year. So conclusion, two options for magnetic confinement, LTS or HTS. LTS bigger is better, and HTS compact reactor is possible, but a lot of challenges for the future years. Thank you for your attention.
Thank you very much. Let's see if there is any question. Online? There are some people who have some questions online. Thank you very much, Professor Bruno Douine. Are there any questions online? So there are some questions.
Yes, just a second. These are from YouTube. Sorry. As tokamaks are pulse machines, would you suggest that 2G HTS must be tested at pulse regime?
Yes, it is. So you need some simulation for many things, but even if in the DC part, you have also ramp to go from zero to the magnetic field, to the current. So you need something AC or pulse field or ramp of fields. So you need to make this kind of simulation.
That's the only question there. That is on media. Yeah.
A discussion here. 2D because you can do 3D models because you take into account the twist, or you can do 2D models as a first approximation. So the question was about if it's necessary to take into account the dynamic of the system. That means if you have to pulse, that means probably the field will change and the HTS will be affected, which is the case. So the reply was yes. Okay, thank you very much, people online. We're going to thank again Professor Bruno Douine, and we have a little thing for you, a little gift from the Institute of Engineering. Thank you very much. And you have a little diploma that you receive as well. Yeah, you can show it. So for acknowledgement of your participation with us today, thank you very much. Thanks. We see each other in a few minutes because we start at 12 Mexico time with Professor Loïc Quéval from France, from Centrale Supélec, the University of Paris-Saclay, France, on superconductivity and railway applications. So we see you in a few minutes, and it's going to be online. Thank you very much. See you in a few seconds, a few minutes. Thanks. Luis, ¿me puedes dar acceso? ¿Me puedes escuchar para indicar que en 5 minutos empezamos?
Hola, Pedro.
Ok,
Ya
perfecto.
está conectado aquí el
Ok,
profesor
el feed
Loïc.
está. Ok, perfecto.
Sí,
Hecho. Entonces vamos a empezar en 5 minutos. We're going to start in 5 minutes. Thanks. We start in 2 minutes. Welcome anew. Thanks for being here. We will have a second talk from Professor Loïc Quéval from the University of Paris-Saclay, the School of Engineering Centrale Supélec. He's going to talk about railways and superconductivity. So we are starting. It's about 12:05 in Mexico City. And welcome Professor Loïc Quéval at the Institute of Engineering, but online. Thank you, Professor Loïc Quéval. The floor is yours.
Hello, everybody. So first of all, I would like to thank the UNAM for inviting me, and especially Professor Trio. Thank you again for giving me the opportunity to give you an update about the Super Rail project, the first commercial superconducting power system being installed in a railway grid. I want to thank all the colleagues that are listed here that are participating actively in this project and that provided the information that I'm presenting today. So this is the content of today's presentation. I'm going to talk about the motivation of the project. I'm going to show you some results about the qualification of the Super Rail HTS cable system.
Sorry, Loïc,
I will show you the
one
type
second.
testers.
Sorry, Loïc. We don't see your presentation, so just to make sure that we can see your presentation. Did you share it? Yes, okay, we can see it. Sorry about that, of the interruption. We can see it. Go ahead, please.
Hello, everybody. Thank you for giving me the opportunity to present you the Super Red project, the first commercial superconducting power cable system for the railway grid. I want to thank the people at UNAM for inviting me. And I want to thank my colleagues who provided all the information that I'm going to present today. This is the outline of the presentation. I'm going to introduce the motivation of the Super Red project. I'm going to show you some experimental results about the qualification of the Super Rail HTS cable system before installation. I will show you the type test loop that we tested in the lab and the type test results. Then I'm going to show you some photos about the ongoing installation of this system in Montparnasse traction substation in Paris before concluding. So let's go back to the motivation of this project. The motivation is the need to increase the rail traffic in densely populated areas, such as Paris, to meet carbon emission reductions targets by 2030. We have electric trains, so if you want to increase the rail traffic, you need to increase the electricity. You need to increase the electric power. So the SNCF, the French railway operator, gave us a practical case study, very concrete. They want to reinforce the electric power of Paris Montparnasse train station. Paris Montparnasse train station is located here at the heart of Paris. This is a big train station with 28 tracks, 200,000 passengers per day, and 750 trains. Today, the traffic is 50 million passengers, and it's going to increase up to 90 million in 2030. So SNCF needs to reinforce the electric power supply of this train station. To do that, they need first to install 4.5 megawatt of nominal power. Since the train station is operating at 1,500 volt DC, it means they need to bring 3,000 amp. But it's a little bit more complex than that, because for train operation, you need to handle inrush power. Inrush power corresponds to the train acceleration. Each time a train starts, there is an inrush peak. This inrush power is 10.5 megawatt. It means that the current peaks are up to 7,000 amp, and they are repetitive each time a train starts. But even more difficult, the fault current is going to be around 67 kilo amp during 100 milliseconds. This is very difficult set of requirements for cable. So let's have a look at the geography of the train station. The train station is located here, where we have the blue marker at the center of Paris. And the traction substation, meaning the electrical substation that brings power to the tracks, is located here, where we have the red star. Actually, the red star is located only 60 meters away from the catenary, meaning that we need to install cables only 60 meters away. You can see here, the red star is located in a building, and outside of the building, you can see the traction substation transformers. Inside the building, you have the power electronic converter to convert from AC to DC to power the 1,500 volt DC grid. You can see too that there is a bridge here, and the trains, they pass above the bridge. So how does today the power goes from this traction substation to the catenaries? Well, it uses a tunnel, and this tunnel is full of conduits. In each conduit, you can install one red cable, such as this one. Each red cable can carry up to 500 amp. In this existing tunnel, we have actually only 2 conduit left. It means that we can only install 2 red cables. It means that we can only install 2 times 500 amps, meaning 1,000 amp, but we need 3,000 amps. So the conventional solution will be to make a new tunnel, to install new cables. So SNCF asked some companies to do that, and the companies responded, well, it's going to be very complicated. because we have limited available space. We have other networks right next to here because we are inside Paris center. We have water systems, we have gas systems, we have telecommunications. So if we make a mistake, we are going to block these networks. And even more complicated, this bridge that is next to the train station and in which you have this tunnel is actually a century-old bridge. And it's very risky to do construction work in this bridge. If you make a mistake, you will stop the traffic of the whole train station for several months or years. So it's very risky, very expensive, and time-consuming to build a new right-of-way, meaning to build a new tunnel. So to solve this problem, we formed the Super Rail Consortium. The Super Rail Consortium is an association of absolute systems that is going to bring expertise in cryogenic machines. Central Supélec and University of Lorraine, we are following this project for the academic part. Nexans with the manufacturer of the superconducting cable, and SNCF with the operator of the train infrastructure. The idea is to use these two existing conduits to install two superconducting cables. And these superconducting cables, they are designed to carry all the current, these 3000 amps. So let's have a better look at the proposition. What we need to do is to install these two superconducting cables in the existing conduits. So we need to use existing conduits. There is here a 3D rendering of the traction substation, the century-old bridge, and the railway tracks of the train stations. And there is a blue line here between the traction substation and the catenary. And this blue line is the existing conduits. You can see that it's not straight. You have some bendings, and you need to go from downside the bridge up to the bridge. So we need to use these existing conduits. They have sharp gradients and turns, and we need to do this installation ensuring continuous operation, meaning that we cannot stop the traffic in the train substation. After the operation, we need to be able to give this system to the train operator, and they should be able to operate it in a simplified way. So this is a big challenge. To do so, Nexans designed this superconducting cable. This superconducting cable has several layers. I'm going to describe them from the inner layer to the outer layer. The inner layer is a former made of copper. This former is here as a mechanical support and to handle the short circuit current. During short circuit, the current is going to go through this former to protect the cable. Around this former, you have two layers of superconducting tapes, Redco tapes, high temperature superconducting tapes. During normal operation, these two layers of superconducting tapes, they carry all the current. Around these two layers of superconducting tapes, you have insulation, dielectric insulation. In this case, this is a PPLP. And outside of this insulation, you have a copper screen. This copper screen is here for protection as well during short circuits. This cable core is immersed in liquid nitrogen. And this liquid nitrogen is flowing along the cable. It is going to be pushed by a cooling machine and is going to be cooled down at the end of the cable. This former, this copper, this superconducting cable core and this liquid nitrogen is inside a double layer cryostat that is fabricated by Nexans as well. Here are the electric parameters of the design cable. The nominal voltage is 100-500 volts because this is the voltage of the train substation. Each cable nominal current is 100-500 amp, 1500 amp. We are going to install two cables, meaning a total of 3000 amp in line with the requirements. The inrush current for one cable is 3500 amps, multiplied by 2 is 7000 amp in line with the requirements, meaning that the cable must be able to handle the nominal current and the inrush current and stay superconducting. It means that the critical current of this cable is more than 4000 amp. And this cable has been designed to sustain a fault current of 67 kOhm during 100 milliseconds. Here is the geometric parameters of this cable. The outer diameter of this cable is 64 millimeters. This is smaller than the 80 millimeters that were required so that we can actually take this cable and put it inside the existing conduits, which are 100 millimeter wide.
Or something else.
The minimum bending radius of this cable is 1.5 meter. This is in line with the requirement so that we can use the existing conduits with the sharp bending ingredients. And the length is 2 times 60 meters. We are going to install 2 cables of 60 meters. As part of this project, Nexans installed a production line in Bourg-en-Bresse, in France, and this is where this cable was produced. You can see here the winding machine, and you can see here the winding of the cable in process. You have here the superconducting tapes that are being wound by this machine around the copper fiber. So I'm going now to show you some results about the qualification of the super rail cable system. Let's start by the type test loop. The type test loop is a system that is representative of the cable system in general. This type test loop has been installed at SNCF Railway Test Agency. This is the laboratory of the SNCF. You can see the type test loop here. It consists of 2 cable pieces. The first cable piece is here, up to this part, and the second cable piece here. 2 terminations here and here. These terminations, they are here to connect the superconducting cable to the normal grid, and 1 joint. The joint is here. This joint is not required for the super rail installation in Paris-Montparnasse, but it has been qualified for future installations. So this system, together with the liquid nitrogen tank, the liquid nitrogen circulation system, and the control cooldown system, constitute the super rail cable system. Let's have a look at the schematic. You have here the first termination of the cable. You have here the superconducting cable inside this cryostat. You see the joint here. And we go back to the second termination. To cool down this cable, we have a liquid nitrogen tank here that is filling a liquid nitrogen circulation squid. This squid is actually a pumped bath. We pump here so that we can decrease the temperature. So we are going to operate at less than 77 Kelvin, the boiling point of liquid nitrogen. We are going to operate around 70 Kelvin. Then we exchange this power with a circulation loop that goes here through the heat exchanger using the liquid nitrogen pump to push the liquid nitrogen inside the cable here and to come back here. And this system is plugged with a cool down system so that we have automated cool down and warm up. Here is a photo of the liquid nitrogen circulation squid. You can see here the cryostat with a pump pass, and you can see here the automate so that everything is automated, operated automatically. Here you can see the input and outputs of liquid nitrogen lines that go from the tank and that go to the cable and from the cable. Here is another view of the installation in the SNCF lab. You have the circulation squid here that is connected to the terminations here and here. And these terminations at the end of the hole, they are connected to the superconducting cable here, up. This is here the joint, and we come back. The liquid nitrogen tank is located outside of the building, behind this garage door. The goal of this type test is to qualify the system before its installation in the train substation. This is the timeline of the type test. We carried out the test in 2 phases. First phase in August 2023 and second phase in April 2024. The first phase included thermal cycles, pressure test, dielectric and lightning impulse, and nominal current test. For the second test, we continued the nominal current test and we measured system losses and pressure drops, and we carried out fault current and recovery time and VI characterization. I want to underline that for this test, we have some applicable standards. For example, all the tests in green, they have applicable standards such as IEC standard or some specific standards for railway grids. But for 2 of the tests, there is no standard. So we had to develop or adapt existing tests. I'm not going to describe all the tests one by one. I'm just going to focus on 2 tests that are, from my point of view, very interesting and unique. This is the first time from my knowledge that we are carrying this kind of test on a full-scale superconducting cable system. The first test is the fault current and recovery time. The idea is to measure the cable behavior during a short circuit and to measure its recovery time to superconducting state. To do that, we need to obtain the short circuit current. Following the requirement, we needed to test the cable for a short circuit of 67 kA during 100 milliseconds. This is actually very difficult to obtain, even in the lab settings. So to do that, we had to use an existing traction substation that is installed in this SNCF lab. This traction substation is directly connected to the RTE, the transmission system, at 63 kilovolts. It consists of a transformer with 1 primary and 2 secondary, feeding a 12-pulse diode rectifier. In series with this 12-pulse diode rectifier, we have a circuit breaker, a short circuit switch, and a load resistance. And then we feed the current inside the cable core in red. At the end of the termination number 2, we short-circuited the conductor and the screen, so the current is going to come back from the conductor to the screen, inside the screen, and come back to the traction substation. So to start the short circuit, we close the short circuit switch, we control the short circuit current using the load resistance, and to open the circuit, we use the circuit breaker of the traction substation. This is what would happen in the real setting in the train substation. And we measure the current and the voltage of the cable. These are the results for different short circuit currents, 5 kA, 10 kA, 18.5 kA, and 40 kA for 200 milliseconds. What I plot here is a duration after the fault at 5 minutes. And in the x-axis, I'm plotting the outlet termination temperature, the temperature outside at the end of the cable. So before the fault, the temperature of the cable is somewhere between 72.5 and 73.5 Kelvin. And during the fault, you have an increase of a few Kelvin, even in the worst case 40 kA, 200 milliseconds. And you have a recovery time. And then we recover the normal state, the operating state, after about 10 minutes. So it gives you an order of magnitude. After a fault, even the worst case fault, you can operate in the normal condition after 10 minutes. Actually, you could continue operating even very quickly after the fault because the cable is still superconducting, but you need to ensure that you don't have any problems. So there is no resistance increase of the loop after testing, and we checked that the integrity of the system was unchanged after the test. I'm going to show you a video of this test. You have here the termination of the cable. You have the loop here, the second termination of the cable, and these red cables are all the cables that are necessary to feed this short circuit current to the cable. And we short circuited the conductor and the former using these cables here. I'm going to start the video now, and you can look at the red cable. They will move because of the Lorentz force during the short circuit test. This is the video of the 40 kiloamp 100 millisecond test. You see the cable moved during the test. So of course you need to design your superconducting cable and its accessories so that they can sustain such mechanical forces during short circuits. And this is how we demonstrate, we qualify that this cable system is able to handle all the requirements of real-life operation. Now I'm going to show you a second test, very interesting from my point of view. The same thing, it's the first time that it was carried out in a full-scale superconducting cable system. The idea is to measure the VI characteristic, meaning I want to measure the resistance of the cable. Of course, it's superconducting, so I expect to measure nothing up to a certain point, which is the critical current, as described in previous presentation by Professor Douine. So to do that, I'm going to use a DC current source of 10 kiloamp, and I'm going to push this current through the conductor of the cable, coming back from one termination to the second termination. And I'm going to measure the voltage of the cable and the current of the cable using a shunt resistance. These are the results. In the x-axis, we have the current from 0 to a little bit less than 9,000 amp. And in the y-axis, you have the voltage. I remind you that the resistance V equal Ri is the slope of this curve here. So between 0 and somewhere 4,000 amp, we have very small slope. We are superconducting. Actually, we don't have a zero slope. We have a small slope, a resistive component that corresponds to the terminations. The terminations, they have copper parts inside. So we are actually measuring the resistive components of the terminations. They are here. And after a given current, somewhere around 5,000 to 6,000 here amp, we start to see an increase of the slope, so we start losing superconductivity. The critical current is well above the 4,000 amp, as specified by the set of requirements. So I want to underline here that the nominal current, which is 100, 500 amp, and the inrush current during the train starts, which is 3,500 amp, is well below the critical current of the cable. So during nominal operation and inrush operation, the cable is staying superconducting. During fault current, we are losing superconductivity and the current is passing through the copper former. We measured no degradation of the critical current after all the tests, including the fault current, meaning this curve was measured after the fault current test that I showed you before in the video. And this demonstrates the high robustness of the superconducting super rail cable system. Here are the key findings of these tests. For the thermal cycles, the system withstood 5 thermal cycles. This is equivalent to a 40-year lifespan. For the pressure, it handled pressure up to 18.5 bar. This is well above the requirements. We successfully passed the dielectric and lightning impulse test. We show stable performance at 100, 500 amps DC during 30 minutes, which is well above the requirements. The system losses and pressure drop were measured, and it confirmed the sizing of the cooling system that is to be installed in Montparnasse. And for the fault current and recovery time, we showed that the cable system can recover within 10 minutes after a fault current up to 40 kiloamp for 200 milliseconds. This is not exactly equal to the standard, because the standard, the requirement was 67 kiloamp, so higher, but for a shorter time. But 40 kiloamp, 200 milliseconds, it ISO I2T to 67 kiloamp, 100 milliseconds, meaning about the same energy deposited. So it suggests this test that it should go well in operation. And finally, we carried out the VI characterization of the cable system. It shows no degradation of the critical current after all these tests, including the fault current. So the test confirms that the cable system meets its design specification. And finally, I want to show you some ongoing information about the installation of this cable at Montparnasse traction substation in Paris. So where is it exactly going to be installed between the traction substation and the trains? Well, this is the traction substation here, and this is the trains here. Let's first follow the path of the electricity, of the current. We start from the plus pole of the rectifier here. We go through the cable A, through termination A here, and we power the feeder, the catenary of one train, and then the current comes back by the rail, comes back up to the negative pole of the diode rectifier. This is for the path of the electric current. So the two cables, they are connected in parallels between the positive pole and the catenary. The return current is through the rails. Let's now follow the flow of liquid nitrogen. We start by the liquid nitrogen tank. We fill the cryogenic squid. We are going to pump it to decrease the temperature of liquid nitrogen, and then using the heat exchanger and the liquid nitrogen pump, we are going to push liquid nitrogen through the cable, through termination 1, A1, through cable A, termination A2, and then at the end, on the platform side, on the catenary side, we loop back and we come back by the second cable. This is one of the main reasons we installed actually 2 cables, so that we can have one inward flow of liquid nitrogen and one backward flow of liquid nitrogen. Actually, it would have been totally feasible to use only one superconducting cable to carry all these currents. It's totally possible with superconductivity, but doing that, it simplifies the operation of the liquid nitrogen circulation. I'm now going to show you some photos of the pooling of the superconducting cable inside the existing conduits. The cable was produced in Bourg-en-Bresse in the Nexans winding line. It was installed on this truck and it was delivered next to the traction substation. And then the cable was pulled in the existing conduits here during the night so that we don't disturb the operation of the trains and of the station during the day. You can see here some operators were guiding the cable to enter in the conduits, and you can see here some existing copper cables. So the superconducting cable is installed in the same tunnel, as the copper cables, but in a different conduit. And it goes outside of this tunnel. On the platform side, you can see a train here, and it's being connected to the catenary at this level. This is here 2 photos of the terminations. We have 2 sets of terminations. We have terminations on the traction substation side here. This is these terminations. These terminations, they are installed next to the bridge here. There is a very small available space, so they are very compact. So you can see the terminations here on the traction substation side. And then you have the second set of termination next to the railway tracks to connect to the catenary. There are these terminations here on the platform side next to the trains. And you can see here more or less the scale of this termination compared to a human operator. And finally, the cooling machine. The cooling machine was installed recently. It was produced by Absolute System and delivered on site with a truck. And it was installed on a platform next to the traction substation. This is the traction substation. Then it was connected here. This is the input and output of the cooling machine here to the cable system. So you have 4 cryogenic lines. You have 1 cryogenic line that comes from the liquid nitrogen tank and enter in the cooling machine so that we subcool it. Then we push the subcooled liquid nitrogen into the cable systems. It comes back from the cable system inside the cooling machine. And then we have here a 4th cable here that is to dump the liquid nitrogen in case of problem. And finally, this is a photo of the termination on the cable on the platform side next to the catenary. You can see the trains here and here. And this is ready for commissioning. We installed some cables to do some testing. So this is being tested before connection to the catenaries to feed the trains. This brings me to the conclusion. Here's the timeline of the Superrail project. We started in 2022. We started with civil engineering work at the Montparnasse train station. We manufactured the cable in 2023. We pulled a fake cable, a dummy cable, in the existing conduit to make sure that everything was okay before pulling a real cable in April 2023. We installed the test loop in SNCF lab in June 2023. We made the first series of tests in August. Then we pulled the real cables in October 2023. We made the second series of tests in April 2024. Then we installed the terminations in end of 2024, December last year. And this year we did some civil engineering work to install the cooling machine, and we installed the cooling machine. And right now we are commissioning the system. Everything is ready, is being tested, and we should be able to plug it to the train to power the train with superconducting electrons by the end of this year. In conclusion, SuperRail demonstrates how superconducting technology can overcome the limitations of conventional solutions in dense urban power grids, thereby increasing public transport capacity and supporting national carbon emissions reduction strategies. Despite some delays caused by the Olympic Games, the project successfully overcame all the challenges associated with installing superconducting cable in the center of a large city such as Paris. This is the world first installation. And SuperRail paves the way for future reinforcement using superconducting cables of the French national railway grid in collaboration with SNCF. In parallel, research and development efforts are continued to drive system improvements beyond the project completion. Before thanking you, I want to underline that as part of this project, we at Laboratory GIPS, Centrale Supélec Paris-Saclay, we had 2 PhD students working on next generation technologies that could be coupled to this kind of system, and they are going to defend their PhD thesis at the end of this month. The PhD defense of Yasmin Baazizi is going to deal with the development of a cryogenic power electronic converter for traction substation, and the PhD defense of Floro Ferreira is going to deal with a superconducting railway traction substation, meaning we want to use a superconducting transformer integrated with a cryogenic direct rectifier and connected to the system. The PhD defense date is 28th of November. It's going to be at Centrale Supélec University of Paris-Saclay, but of course, you can follow us on LinkedIn to get the link and attend this presentation by video conference. Thank you very much.
Thank you very much for this nice presentation. Do we have any questions? No, it seems that here physically not so much. Online, do we have any questions online? Do we have anyone that have any question online? Or you can write in the chat as well, or in YouTube as well. You can write there. No, I don't know. Do we have any question online? Nobody answers me, so I guess we don't. Huh? No, we don't. So I have just a question, Loïc. What is the next step? I mean, now you have a cable installed in a station, railway station in France. Is there anything other than that is in plan, or some ideas that is floating around in France, other than the fusion? Because I mean, Bruno told us there is the fusion, but there is something else, or not?
So actually, I will say that to install a cable in a real commercial operation is the first step. And actually, maybe this is a difficult step, but this is not the most difficult. The most difficult step is going to keep this cable in operation for many years, monitor it so that the whole community can learn about this. We need return of experience about this cable. As you know, the longest cable operation was the Ampacity cable in Germany. It was operated between 7 and 9 years, depending on how you count. And it was decommissioned at the end. So we don't have so much return on experience on this kind of system. So yes, the next step for this SuperRail project is actually to monitor this cable for a long time so that we learn all as a community about this system, so that we prove that it's reliable. If it's not, if there are some problems, we need to be able to learn about it, to fix it, so that we can make it a sustainable solution for future installations. So this is the first step, to monitor this cable.
Thank you very much. I have another more technical question, and maybe I missed it. is about the amount of current, the margin in current you have in this kind of cables. Is it a specific cables, or this is a cable that can be used in any other railway, for example, or this is really specific, it has been specifically designed with this amount of current for this specific application, or we could say that there is some kind of generality to this cable that can be used somewhere else.
So the specification for this cable, they come from SNCF. They are a standard set of specification for cable systems in general, whether it's superconducting or not. You need to carry this nominal current, this inrush current, and sustain this short circuit current for that amount of time. So the specifications, they are generic. And we designed the cable so that it can meet this specification. So after qualification, which has been done, this cable can be installed in Montparnasse or in any other railway grid in France. If a railway operator outside of France has other specifications, maybe we'll need to do some complementary qualification test, or maybe we'll be happy with those tests already. So the response is no, this is a generic cable that can be installed without new testing, new development in any railway grid that meets this kind of specification.
Nice. Another question. I see that you put out the VI curve, no? But do you know the margin current? Do you know where they are, like 50%, 40%, or this is something that hasn't been shared? Sorry.
I cannot share all the information, but I can share this curve in front of you. But you can already see many interesting information from my point of view. The first one is the resistive component here that corresponds to the termination resistance. It shows you here that you don't really have a polar law form. You have some kind of double exponential. You have a first knee here and a second knee here, because we have actually two sets of cable in the test loop. We have a longer set and a smaller set, and they are made with different HTS tapes. So maybe you can see the influence of these two designs, these two tapes here. Okay, so it gives you some really useful information still anyway.
Thank you very much. Last question on my side. Sorry, the one. We are working on the modeling cable, so it goes in that direction. Did they do any modeling or specific studies, like numerical studies of the behavior of this cable that you know of? And is it necessary to do this kind of studies in addition to experimental work and test? Do you think, in your opinion, that modeling this kind of cable to see what can happen in the network is of interest?
So the first question is about modeling. If some models, numerical models, were made as part of this project, the response is yes. It was a work package of my colleagues, Kevin Berger at University de Lorraine. One of the PhD students developed models and used the data from the qualification test to validate these models. And some results have been shared to the community in some publications. So yes, we developed some models and we used some of the test results to validate these models.
Yeah,
the second question is about...
Loïc, I wasn't very precise. Do you know if they did some modeling on the network side, not just the component, but on the network?
No, as part of this project, there is no modeling on the network side, on the power grid side. It was modeling on the component side, the superconducting cable behavior from between the traction substation and the catenary. No power system analysis. So the second question is about, do we need actually to do this kind of models? And then I understand, do we need to do calculation at the power grid level using this kind of model? The response is yes, definitely. First, you need to have models, but you need to have them validated. This is why this is so important to have this kind of real-world data and to be able to share some of them. Of course, some data we cannot share, but still we can use the validated model to carry simulation and estimation. Why is it important? because it gives you confidence when you want to try a scenario, how it's going to behave. Since it's a new component, a simulation with a validated model will give you a first hint how it will behave in your grid, and if something is going to happen or if it's going to behave as expected or not. So yes, this is very important. It gives you trust, makes you think. It will help you maybe to think if you need to change your protection strategy or to adapt something in your grid. Actually, it's not obvious at all what will happen when you integrate a superconducting cable in a meshed grid. This is not the case here, but in a meshed grid, like they are planning to do in Munich, in the Superlink project in Munich, it's not obvious at all what will happen. And so they carried some grid level analysis in that direction. So yes, it's very important. It gives you some hints at how it's going to go.
Thank you very much, Professor Loïc Quéval. Thank you for your participation from France, but you are always welcome here at the Institute of Engineering. I think we can thank the speakers again, including Professor Loïc. I have a gift for you, so I will bring it with me, obviously. So thank you very much to all the speakers again. And we hope to see you soon. Thank you, Loïc. Have a nice evening in France and see you soon. Bye-bye. Thank you, everybody. Thanks for the participation of everyone. And we hope to have this event next year with some new speakers on the foundation of electromagnetism, and its application. So see you soon. Keep in touch and have a nice day and nice evening. Bye-bye.